In the previous section, we talked about the relative velocity between 2 points on a rigid body. In this section, we are going to extend it to relative accelerations between any 2 points of a rigid body. Let's say we have these 2 points on a rigid body, point A and point B. And if you remember from chapter 3, the relative acceleration between any 2 points, they don't have to be on the same rigid body, is this. Acceleration of B is going to be equal to acceleration of A plus acceleration of B with respect to A. Now, if if both of these points will be on the same rigid body, then acceleration of B with respect to A is going to be something specific. Again, just to imagine what is the meaning of acceleration of B with respect to A, just imagine A is pinned to the ground. A is not moving. Now, what's going to be the acceleration of B? If the rigid body is rotating with angular velocity of omega, and let's say the angular acceleration of it is alpha, if we pin A down to the ground, then B is going to rotate on a circle about A, right? So if you remember, whenever we have a point which is moving on a circle, then it's going to have two accelerations. Acceleration in the tangential direction, the equation for that was r times alpha, and acceleration in the normal direction toward the center. The magnitude of that acceleration was r times omega squared. So just to remind you, acceleration of B with respect to A is going to have two components. The tangential part, which is alpha cross r, or AB here, and also acceleration in the normal direction was omega cross r, which is AB here. And also we said this part, which has two cross products, you can replace it simply with negative omega squared times r as a vector, which is AB here. Instead of doing these two cross products, we can prove that's equal to this. As long as our rigid body is moving in a plane, then these two are going to be equal. So if I replace it in this general equation, acceleration of B is equal to acceleration of A plus alpha cross AB minus omega squared times AB. So this is the relative acceleration between 2 points on a rigid body. Now, why this is useful, you're going to see in a lot of examples that we can analyze accelerations of different points on the rigid body using this equation. Okay. Just to start, let's just start with this simple problem. So here, problem 98 in chapter 5, we have this rotor. This rotor is rotating about point. These two blades are rotating about point O with angular velocity of 2 radian per second, which is constant. So theta dot, or omega, is given. It is 2 radian per second. And it is constant, which means angular acceleration of these blades is equal to 0. And in the same time, the motor itself is moving in the x direction with a constant acceleration of a knot, which is equal to 10 feet per second squared. And the question is, what is the acceleration of the tip of this blade? So we know acceleration of O, 10 feet per second squared to the right. We know the angular velocity of this blade, and also the angular acceleration of it is given as well. It is 0. So to find the acceleration of this point, we can simply use the relative acceleration equation between A and O, which we just talked about it. So let's write the equation first. Acceleration of A is equal to acceleration of O plus alpha of the rigid body, which is this blade, cross OA minus omega squared times OA. Okay. We have this part is 0 because alpha is 0, omega is given, and we know what is OA in a vector form, right? By replacing all of them here, we are going to be able to find acceleration of point A, this point. Acceleration of O is given in the problem. It is 10 feet per second squared in the I direction, and is constant, minus omega squared times OA, and omega is given as well. It is 2, so I'm going to have negative 4 times OA. And OA is a vector, which we can simply write it in the vector form, right? 32 inches divided by 12 to make it fit. So times 32 divided by 12 times the direction of it, right? Which is going to be cosine of theta in the I direction and sine of theta in the j direction. And that's all. This problem is specifically asking about 3 different conditions: when theta is equal to 0, when theta is equal to 90 degree, and when theta is equal to 180 degree. You can replace all of those angles here to find acceleration of A. So this is going to be the general solution for this problem.